implementation? Oh, yes. Do you want to mention? We're going to kick off the technical part of the talk with the probably highest level talk about ZFS. So thanks to Kirk for coming and giving a talk that he's given before about the introduction to the implementation of ZFS. Hopefully this sets the stage and helps you to frame some of the later, even more technical talks that are coming after this. Thanks a lot, Kirk.
Thanks. So this is Groth the goat. He's the mascot of the BSDs. He's been to 10 countries on 4 continents over the last 2 years. He's just back from a BSD conference in Brazil. So he's now made it to ZFS. I think this may be his first trip to a conference in San Francisco. Anyway, it's somewhat intimidating giving this talk because there's at least half the people in the room that know far more about ZFS than I do. So, be kind with your questions. My goal is really to give you a high-level overview. I normally do this lecture in 2 hours, so we're going to go a little bit more quickly. So let's start with a complete overview here. The technology is what they call non-overwriting, or once you write a block onto the disk, it stays there. If any modifications are made, a new copy is made elsewhere. You do not overwrite the existing block. File systems, up until the non-overwriting style of file systems, would rewrite things all the time. So you would, you wanted to change the mode of an inode, we'd read it in and off the disk, we'd make the change, and we'd write it back on top of what was there before. The problem with that is that if you're not really careful about the way you do the writes, the file system can become inconsistent, and it's always a little bit inconsistent if writing is going on, and so you usually have to do some kind of journaling or logging or soft updates or whatever in order to keep it in a consistent state. With a non-overwriting file system, the file system is always consistent. It just moves atomically from one consistent state to the next consistent state each time you do a checkpoint. Now, you have to keep some kind of a log or journal between each of the checkpoints so that if if something happens after the checkpoint and before you've taken the next one, you're going to be able to recover that. In particular, there's the fsync system call, which says, before this system call returns, I want this file to be consistent on disk. And you can't do that by taking a checkpoint, because a checkpoint is too heavyweight, as you will see, to be doing hundreds of times a second, as you often have to do at fsync. And so you do need to have a journal that's going to keep track of what happens between those checkpoints. But the only recovery is to start at your last consistent checkpoint and then just roll through the journal. And as long as you don't let the journal build up for too long, you can bound the amount of time it takes to get going again. Other things that come almost for free with a non-overwriting file system are snapshots. You essentially just take a checkpoint, and then instead of just throwing away the previous one, as you normally would, you hold on to that as more checkpoints are made in the future. And so, there's some other little magic that has to happen, which we'll talk about a bit. But at a sort of a high level, you just take a checkpoint and then save a copy of that checkpoint. And as long as you don't reuse any of the blocks that are part of that checkpoint, it'll just stay there. Also, clones are very easy. You take a checkpoint, snapshot, and then you just start making changes along that line. And if you decide, oh, I want that to be the file system now, you can just say, all right, well, that's not the head of the tree. This one down here is now. And so, again, it's conceptually a very straightforward thing to do. And in ZFS, in particular, the snapshots and clones and so on are plentiful. There's no particular limit on the number of them you can have, modulo how much disk space you have, because they're going to take some amount of space to keep them around. Okay. The other thing about ginormous file systems, we start talking about multiple petabyte file systems, is that hardware, you might find this hard to believe, can be flaky at times. And so in order to cope with that issue, you need something beyond just sort of hoping. And so there's a lot of metadata redundancy, there's data checksums, and this allows recovery at a number of levels. So you can detect when bad things have happened. With the redundancy, you can essentially recover from one of the redundant copies. And then beyond that, behind that is sort of a backstop, you have RAID Z, which can then give you further correction. So there's a huge amount of effort put into making sure that you are never in the state where it's like, oops, we just lost the file system, sorry. You can go get it from your possibly non-existent backups. All right. We have selective data compression and deduplication. The problem with deduplication is you need a deduplication table more or less in memory. I mean, in theory, you can have it on disk, but it brings new meaning to save-day service if you do that. So if it doesn't fit in the memory, then it's more or less useless. It doesn't make sense to necessarily deduplicate your entire umpteen million petabytes. It may be just the VMs that you want to do that with. And so ZFS allows you to say, all right, that stuff should be deduplicated, but the rest of it do not do that. Same thing with compression, and in fact, you can use different compression algorithms because different algorithms work on different kinds of data in better ways. Another huge step forward is the notion of a pooled storage. And by that I mean there's just a big pool of storage and you have a bunch of file systems and any file system can claim memory out of the pool. Historically, we had the requirement that you say how big the file system is going to be when you make it, and if you didn't make it big enough, you couldn't like say, oh, could I get some space from that one next to me? Like, nope, sorry, can't do that. So the pooled storage, again, was a huge step forward. I already mentioned that you have RAID Z, and then you can have single, double, or triple parity, which means you can lose 1, 2, or 3 drives and still recover it. Pooled storage is great, but it's, socialism goes just so far. The problem is that the poor people want all the space, and the people that are buying all the space want to make sure that they have space. So you have to bring a little capitalism to the market. And so that's done with the space management. You can put quotas, which says, notwithstanding the fact that I've got a petabyte in the pool, this particular individual over here is not allowed to have more than 50 terabytes. Or conversely, you can say, these logs over here are absolutely critical to the security of my system, and I want to reserve and make sure that this file system is always going to get 100 terabytes no matter what. Both of these things can be implemented. And there's then fast remote replication and backups, which I'm not going to say much of anything about, but you will undoubtedly hear something about that later today. Okay, so let's get into the organization here. At the very top, we have the Uber block, which is, you can sort of think of as the super block, although historically a super block was for a file system. This is for the entire pool. Below that, you have this thing called an object set, which in this case, at the top layer there, the meta object layer, is keeping track of all of the things that are in the pool. So you have all your snapshots, all your zvols, all your file systems, all your clones, etc. And in these pictures that you see, anytime you see something that has like sort of triangle going down to a big array, that really just means that we're using indirect blocks. So that array of things can be however big we need it to be. So just like in historic Unix, you had a file and you can just keep making it bigger and bigger and bigger by building up the indirect block structure. The same thing is true here. So the thing that are under the object set there, that array is just made as big as is necessary. In ZFS, usually the first object in the array is a master object, which is where you keep stuff about that particular thing. And in the meta object layer, the top layer there, we also have the space map because that's where we're actually keeping track of the blocks that are free and the blocks that are being used among all the different file systems. So normally space maps are down in file systems. Here it's up in the pool because the pool is the level where we're managing the blocks. So then the example here, I've taken one of the file systems. It again has an object set, and this is an array of what we would historically sort of think of as inodes. So it's all the things that make up the things that are in the file system, so directories and files and symbolic links and so on. And again, you just make the array bigger if you need more files, and nominally you could shrink it if you needed to. You get some sort of Swiss cheese look in it, but if you needed to, you could shrink it. And then again, in an example I have in this picture, you have the file. And again, it's just an array of user data, just like any traditional file that you would see in a file system. And using indirect blocks, it can get sort of arbitrarily large. So let's look at some of the little bits of technology that are in ZFS. Let's start with the ZFS block pointer. One of the ZFS developers described this to me as the Titanic of block pointers. To give you an example, in the original UFS, a block pointer was 4 bytes long. And when we revised the file system to deal with bigger disks and bigger file systems, we went, woo, all the way to 8 bytes per block pointer. And people, oh, think of all the wasted space. Well, this puppy's 128 bytes, every block pointer in the system. And you say, well, what are you doing with all that? It turns out this is where a lot of the redundancy and other integrity stuff comes from the block pointers being this large. So you'll see there's pairs here. So VDEV1, grid, A size, offset 1, and 2, and 3. And these are pointers to actual disk blocks. Actually, VDEV tells you the device it's on, and the offset's the offset on that device, and other bits and pieces that I'm not going to go into detail here. But there's 3 of them there. So anytime there's metadata in ZFS, so for example, when you've got a set of indirect blocks, they are always at least one set of redundancy. And normally, file content is not redundant, but you can ask ZFS to keep it redundant. And if it does that, then you'll have 2 pointers to 2 different blocks for every block pointer that makes up the file. And for any metadata associated with that file, you'll get 3 copies made. And ZFS will generally try and make sure that those redundant copies are on different drives at a minimum. So in sort of the usual form, if it's metadata, at least the first 2 of those are going to be filled in. If it's end user data, at least 1 will be filled in. But it can go to 2 and 3, as I said, if you've requested a higher level of redundancy. We then have a whole bunch of things. The checksum algorithm we're using, compression algorithm that we're using. There's the physical size of the block and the actual size and the logical size. And that, the sizes can be different if it's compressed versus what it is when it's uncompressed. And on disk, it may not actually manage to all fit in a contiguous chunk. And so there may be essentially a little block at the front that tells where the other pieces are. And so again, it can the actual size that's out on disk could be a little bit bigger, and it also may have RAID checksum blocks associated with it as well. Okay, we have a physical birth time, and that is the checkpoint at which it came into existence, and that's, as you'll see later, is important in trying to decide when we can free it up. And then if it's part of a deduplication, the thing that it's deduplicating may have come in at a different time than the actual block did, and that's why we need the second time field. And then the last 4 here are the checksum. And the checksum for the block is not stored in the block, it's stored in the block pointer. And so if the block gets corrupted in some way, we can still tell. If you put the checksum in the block, then some errors you will not be able to detect. So for example, sometimes you send a block to a disk and it doesn't end up where you told it to go because the parity line or the address lines somehow bounce as it goes out to the disk. So the disk thinks it's doing the right thing, but it puts it in the wrong place. If it had the checksum in it, when you read it back, you'd think it was fine. But this way, you'd read that thing back. It's like, no, that's not fine. So having the checksum not stored with the block, but rather stored with the block pointer, gives you some extra levels of safety. All right, let's move on to the block management. The disk blocks are kept in a pool, as I've already said. The multiple file systems and snapshots are also associated with that pool. The blocks from the pool are given to the file system as they're needed and reclaimed when they're freed. When they're freed turns out to be, that's sort of the little magic secret sauce that makes ZFS work, and I am going to talk a bit about that a little later. And then you can, as I said, reserve space to make sure you have it in the future, and put quotas on things to make sure that people don't use too much space. So let's take a look at that picture again now, but in a bit more detail here. So you can see that the object set there up at the meta offset layer, which is just often referred to as the moss layer. So when you hear people talking about moss, they're not talking about stuff that grows on rocks. They're talking about this top layer here. And so many of these things end up having one or more D nodes associated with them. D node is sort of like an I node on steroids, so it keeps track of, among other things, the sort of the indirect blocks that are describing the thing that this is describing. And so here you can see that array that makes up file systems and so on actually is a little more detailed than that. So you have, for example, where we see the pointer towards the right there that says it's a pointer to a file system or a clone, we have a direct D node that references that, but then there's also associated with that a directory. And in this case, the directory is kind of tracking other things about that file system, like, oh, well, it's got these other snapshots and clones or other things that are associated with it, along with various and sundry other bits and pieces of data. The thing that it references, the actual file system there, you can see is actually made up of sort of three pieces. It says user quota. It's not really their quota. It's really what they're using. You can have quotas on users. You can have quotas on groups. So there's sort of how much particular users are using and how much particular groups are using. And then you can see the array, which just makes up the files of the file system, directories, et cetera. And you'll see also hanging off the side there a little thing that says ZIL. That's the ZFS intent log. Remember I said we had to have a log that tracked what was going on between checkpoints, and that is that log. And of course, each thing that can be modified has to have an intent log that's associated with it. And of course, later, if we have to do a recovery, we first find the most current stable state of the file system, and then we go into it, and we have to walk through all these objects, and for any of them that has an intent log associated with it, we have to do the roll forward associated with that log. You'll see to the left of the file system here, there's a ZVol. A ZVol is a thing that looks sort of like a raw disk, if you will, except it's a raw disk that has nice properties, like you can take a snapshot of it, you can clone it, and, the usual stuff. And so it has only two D nodes that are associated with it. One is the thing that describes the thing that makes up the raw disk partition, and of course its master node. And unlike most raw disks, if you need it to be bigger, it's like, oops, I didn't make that big enough. Well, just make it a little larger or smaller. You can do that because, of course, the data is all being managed from the pool like any other object in here. You'll see a snapshot to the left of the ZVol there. It looks a lot like a file system because it's really a frozen file system. You notice that it doesn't have the quotas shown there. They actually are there because at some point you might clone it, and so you'd need to know what at that time people were using. But logically, it's not there because we're not making modifications to it, so we don't have to track that stuff. All right, and then you can see the space map and the master node, which hang off of all these things. And again, that's really just sort of a place to put stuff about that particular object. So, next up, how do we go about making a checkpoint? We are going to collect all of the updates in memory. So as writes occur, we're just accumulating them in memory. And then periodically, we need to say, all right, it's time to do a checkpoint. And so we take all of that in-core state that's changed and write it somewhere. And once we've got it all completely written, the very last step is to update the uber block. So the uber block is the only thing that ever gets overwritten. And I use the word overwritten rather lightly here because on a minimally configured ZFS system, you'll have about 5,000 copies of the uber block, and many of which are redundant, but there's essentially 128, or maybe it's 256, I don't remember exactly, that are sort of used in rotation. And so you'll have at least the last 128 or 256 checkpoints copied, across a whole bunch of disks, et cetera. So, at some point in the future, a checkpoint's going to overwrite a very old checkpoint. But in essence, logically, we are overwriting that checkpoint. Okay, but note, it's always the last step. Everything is on the disk. The disk says, yes, it's really there. I'm not lying to you. And, can't always believe disks. But, if you pound on them hard enough, you can say, no, really, I mean it. Okay, now that you've said that everything is on there, and you really have it, now I'm going to write the last Uber block. And writing the Uber block, that moves us, boom, to this new consistent state. Okay, so the entire pool is always consistent. When we do a checkpoint, we're not checkpointing individual file systems or individual clones. We are checkpointing the pool. So everything comes to a consistent point at the same time within that pool. So all the things that are changing, file systems, clones, zvols, snapshots that have been created on different file systems, et cetera. As I've already said about 5 times, we do have to log changes between the checkpoints for anything that needs to be persistent. And the fly in the ointment is fsync, because that's the system call that says, when I return from this system call, I expect the data to be on the disk. And that's critical for things like databases, or even for your editor when you write the thing out. It doesn't actually partially overwrite your old file and then you come back and it's half written. It writes it to a new location. It does an fsync to make sure it's really there, and then it does an atomic rename to move it on top. So you either have the old copy that you were editing or the new copy, but you never get something that's like a mishmash halfway in between. The fsync system call is done a lot. If you're running something like a mail server, every single incoming mail is going to have an fsync occur, because before you go to the other end of the SMTP connection and say, yes, I got it, it's got to be on the disk here. Otherwise, mail would be unreliable, which used to be important. At any rate, hundreds of fsyncs a second is not uncommon, and I'm going to talk about the steps in a checkpoint, and when you see what they are, you'll understand why you can't implement fsync with checkpoints. Okay, if we need to do a recovery after a crash, we start from the last checkpoint, which is kind of interesting because we have to figure out what that is. So we have to look at all 5,000 or 10,000 of the Uber blocks and find the set of them that has the latest checkpoint number. Okay, once we do that, then we go down into that and we find all those intent logs and we roll through them. And then once we've rolled through it, we can create a new checkpoint and we're off and running. In fact, it can do that in parallel with letting you do other things, but I'm not going to get into the machinations of how that works. All right, but let's take a look here at what's actually involved in doing a checkpoint. So this is what would happen if I wrote 1 byte to 1 file in 1 file system and then did a checkpoint. So this is the absolute worst case scenario, because we have to ripple all the way from the way down here somewhere, all the way through all the data structures, all the way to the Uber block. By aggregating a bunch of changes at once, the higher levels only change once per checkpoint, whereas the lower levels are where we're adding the new data. So this is a worst case scenario, but just to give you an idea of what has to happen. Okay, so step 1, we're starting at the bottom here. We've added a byte of data to the file. And potentially that byte, or maybe it's a few bytes, required us to actually add a new data block. And so if we had to add a new data block, or even if we didn't need to add a data block, we could just change an existing data block. But of course, we can't change the existing data block that's already there. So we have to create a new data block. So no matter what, we're going to have to change the indirect block pointer that points to that. And then, of course, that's a whole new block. So we have to change the indirect block pointer that points to that indirect block, blah, 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 in step 2. Every single indirect block up to the dnode that describes the file. Well, of course, that means we then have to update the dnode that describes the file, and we can't do that in place, and so that has to be somewhere else. And so that means that the object set layer there, that array of all the inodes, we have to trickle that up through all the indirect block pointers there 2 or 3 levels, which now means the object set has changed. So we need to make a new copy of that as step 5. And that, of course, means the thing that points to that object set in the MOS layer there, that has to change. And so once that has to change, then all the indirect blocks that describe it all have to be written, which, of course, then means the thing that points to the top of that, the object set there in step 8, has to change. And finally, the uber block has to change. So you can see that adding 1 byte to one file and then doing an fsync and checkpointing it is not going to be sort of a viable thing to do, because it would require the writing of order of, well, depending on how many levels of indirection you have, at least 9 and probably considerably more blocks than that. So that's why we can't just do checkpoints willy-nilly. Now, what actually happens is we do checkpoints after a certain amount of data has been written, but we'll also bound it by time. So if, we haven't been doing a lot of writing, but 10 seconds or something has passed, we'll just decide to take a checkpoint. So the issue here is that the thing that makes non-overwriting file systems complex is the fact that you have to, not overwriting means there's a whole lot of stuff you can't overwrite. And so you need to be able to amortize that across some amount of time. And this is the motivation for having the intent log, so that we can say, well, in the intent log, instead of doing all this, we'll just put a thing in the intent log that says this file should have this byte added to it, because that's just like a lot less to deal with. All right, next topic. We don't want to dwell too long on any one of these topics, because they're all fascinating and can go on for a long time about them. But the next thing I want to look at here is RAID Z. And the Z part of it, why it's not RAID 3 or RAID 5 or whatever, is to indicate the fact that it doesn't have a fixed block size. So in a typical RAID system, you have, let's say, 5 disks, and so a stripe writes across all 5 disks. You have typically 4 that are data and 1 that is parity. And the issue with a standard RAID is if you don't write the entire stripe, let's say you just write the first 2 blocks, then you have to essentially recalculate the parity, and so you have to write those 2, and then you have to read the parity in and update it and write it back and so on. And there's other issues. There's the write hole, which I might talk about a little later if I have time. But the point of RAID Z is that since it's integrated into ZFS, it's all part of the file system, then it means that each time we write something into the RAID, we write just exactly the size that we need and no more. So in this particular picture here, the first block that we've written completely fills the first 2 stripes. And so you can see in that one, we've essentially written 8 blocks, D0, D1, 2, 3, 4, 5, 6, and 7. And then we need a parity block for each stripe, so we have parity 0 and parity 1. Okay, then the next block that got written is the shaded thing that follows that in stripe 3. And that particular one only had 3 blocks associated with it. So there's D0, D1, and D2. And everything that we write, even if it's only a single block, still has to have a parity associated with it. And so you'll see that the parity 0 there, but that's just over 0, 1, and 2. And then we write another 3-block piece, and that's the not shaded one that follows that. So on the very end of the stripe 3 there on disk 5, you see the parity 0, and then its data blocks D0, D1, D2. So you see the parities don't all end up just lining up on drive 1. They just sort of end up at the beginning of each thing that we are writing here. Okay, you see we had a very short one. It's just a single block, so there you have D0 and P0. That's sort of the worst case scenario for RAID Z, and that is when you're doing 1-block writes, because at that point you now have a 50% overhead in the sense that you've got 1 block of data and a parity. And that's assuming you're doing single parity and not double parity, because then you'd have 2 parity blocks. So one of the reasons that ZFS tries to sort of keep blocks at a 16K or larger size is so that they don't have the overhead of the one parity, one data block. And that tends to be one of the weaknesses when you have zvols that use the disk block size of blocks. Okay, so then you can see we have a completely giant block there with, 14 data blocks in it. And then you'll see that it then also has 4 parity blocks. So three full-size stripes, and then the last parity there just goes with the residual 2 blocks. Now, one of the other issues that you'll see occasionally shows up now in the next one here, the one that starts on stripe 8 in disk 4 there. And here we have a 4-block, a block that's of size 4, 4 pieces to it. And if we just did it in a straightforward way, D0, 1, 2, 3, and parity, we would end up with using 5 of the disk blocks there. And if we then freed that, and we could ending up with little pieces that we wouldn't be able to use because it would only be a single piece. So we round that particular one up to ensure that it's an even number of blocks. So now if it gets freed and it gets reused, we'll always be able to have at least 2 blocks that are free that we could put something into there. So anytime you see the X, that's just because we need to round it up to make sure that it, in this case, is a multiple of 2. If you're doing double redundancy or triple redundancy, you would need to have a bigger, you'd have to round up to more blocks. So that's why we occasionally drop in those unused blocks. Okay, so the long and short of it is we have variable size blocks, and we know what the size of the blocks are because we have the block pointers that point to them and tell us how big those things are. The parity sectors on the disk are on the disk that starts the block. So we can see, talked about that. Then if we have 1 parity block, then we can have, in this particular case with 5 drives, we can have up to 4 blocks per parity sector. And the X's are the multiple of number of blocks plus, or number of parity blocks plus 1. All right, so let's talk then, we've got this RAID Z. How do we do the recovery of it? We do it by, we have to traverse all the file systems. So we essentially have to descend, starting from the uber block all the way down through everything and look at all the block pointers in the whole tree because that's the thing that points to where the blocks are. This is fast if your pool is not fully allocated. By contrast, with a traditional RAID system, you lose a disk. You have to walk all the disks that make up the RAID group, reading every single one of them. So if we only have to read 20% of all the drives, then that's going to be faster than having to read all the drives. On the other hand, as the pool gets more and more full, it actually becomes slower than the traditional way because unlike the traditional way where we're just doing sequential reads through the drives, here we're running around because we're following all the various block pointers. And we use the physical birth time to determine blocks that need to be rebuilt, which I'm not going to get into the details of that. But I will say just briefly, the traditional RAID has this problem of what they call the write hole. And simply put, problem is you're updating one of the stripes and you send out, if it's a stripe of size 5, you send 5 I/O requests to 5 drives. And now let's say 3 of the drives have completed their write, but the other 2 haven't, and the system crashes, then all of a sudden, when we come back up, that stripe is just inconsistent. I mean, you read it, and the checksum is, says it's wrong, but it doesn't allow you to reconstruct it because you were sort of halfway through doing it. And so for traditional RAID, you got to have some kind of non-volatile memory or some other technique to essentially be able to recover the stripes that were in the midst of being written. That's never a problem with RAID Z because, yes, you're going to have things that are inconsistent, but we get all that stuff written before we update the uber block. And so by the time we update the uber block and say this is part of the now consistent file system, all the I/Os on all the drives have completed, and so we don't have to worry about making sure that we go back and recover writes that were in progress on a RAID array. Okay, so I said that the secret sauce of ZFS is knowing when to free blocks. And the problem is we've got the bitmap that says, all right, what are the blocks that are free? And so now if we remove a file, traditionally we would put the blocks that were part of that file into the bitmap. But in ZFS, of course, you can have not only the file that's claiming those blocks, but then there may be snapshots that claim the blocks or other clones or whatever. And so we can't actually free a block until anything that's claiming it is gone. Well, there's been sort of an evolution of non-overwriting file systems. So the very first one actually came out of Berkeley, the log structured file system. And in that case, they just used garbage collection. So it was just like periodically, oh, we're out of space, so we'll just run around and do traditional garbage collection, figure out what blocks aren't in use, and put them, make them available again. This caused pauses that did not refresh in the performance of the file system. And so it was really not a long-term viable way to go. I mean, a lot of research was done on how to make it less obnoxious, but at the end of the day, it's just obnoxious. So sort of the next step after that was Waffle. And they chose to take the file system bitmap. Instead of having 1 bit per block, they had an array of bits, so 256 bits. And the first bit was the live file system, and then each of the successive bits was for various snapshots. And so if a snapshot had it, that bit would be set, and when the snapshot was freed, that bit would be cleared. And so when the entire bit array was cleared, then the block was free and you could reuse it. Well, the problem with that is you've got to decide how big the bit array is going to be, and that's the maximum number of snapshots you can have. And, that's kind of lame. So, I mean, it was a big step forward, but it was still kind of lame. So when they did ZFS, they said, well, we don't want to have, arbitrary limits like that. And also, taking a snapshot in Waffle is a more time-consuming process because you got to deal with all the bitmaps. So instead, what ZFS does is keep these things called dead lists, which I'm going to show you on the next slide. So the idea is sort of when a block comes into existence and it gets used for a number of snapshots, and finally the file system releases it. And so instead of freeing it, of course, it sort of passes it down the dead list to the first snapshot that's using it. And if that snapshot goes away, it passes it down to the next snapshot that's using it. And it gets all the way to the end, and there's no one that's claiming it anymore. Then it sort of falls off the end and gets put back in the free list. That's a really hand-wavy explanation. I'm going to give you a slightly better one, but it'll make your head spin. Okay, so a block gets allocated. Its birth time is the current transaction that gets created in. Over time, the snapshots are taken. Then when it finally gets overwritten or truncated or deleted or whatever, the block gets released. And so we then have to have the technique for figuring out when it can be freed. So this picture sums it all up, and I have to thank Matt Ahrens for coming up with this picture, and then I just put some words to try and explain it. I'm going to give you the 30-second run-through, which you can't, if you haven't looked at this stuff before, you'll have a hard time getting, but I have a whole textbook that you can buy that explains it in much more detail. This little promotion brought to you, never mind. Okay, so in this particular picture here, we have three snapshots. So time is going from left to right. So we've got the snapshot that we're focusing on right now that we're about getting ready to free. We've got another snapshot ahead of us, or possibly the active file system next ahead of us. And on the other side of us, we have older snapshots. The snapshots are always kept in a sorted time order, where time in this case is the checkpoint number. Okay, so we're now getting ready to free this snap. And you can see here we've got 3 or 4 blocks we're interested in. We've got block A, B, C, and D. So block A has been being used for a very long time, but it ends, it went out of existence after this snapshot. So between the time this snapshot was created and the future one or the future file system, it got deleted. So nobody newer than us cares about it. So what's essentially going to happen is that for A, we're going to pass that to the left and say, well, we don't care about it anymore, but obviously other people do. We've got block B, where we are, it came into existence just before we were created. And nobody after us cares about it. So block B is going to be the woohoo block that we actually get to free. And then block C is just goes from far before us to far after us, so we don't care about it particularly. And block D is one that went out of existence before us, so other things may care about it. Okay, so we are going to iterate over essentially blocks A and B, which are the ones that we need to look at. Block A was born before us, so it gets added to the dead list, which is going to be passed to our follow-on. Block B was born after it, so it can be freed. And then once we've done all the processing for all the blocks that were passed to us, then we just say, all right, here's our dead list. These are the things we don't care about anymore, and we pass it down the line. And so it'll now be hanging off along with block D from previous snap. Okay, notice in this picture, at no time did I ever say, and then we make a pass over the block allocation map. This is key. We don't have to do that, unlike things that came before us. And so the point is that the cost of deleting these things is essentially the cost of how big that list is. Now, that list can be pretty big, but it is a function of sort of how much churn is going on in your file system. So you can have a large, fairly static file system, and taking snapshots and freeing snapshots is not all that expensive because there's not that much churn, and it's the churn that creates these dead lists. And so again, it's one of those things where ZFS is sort of the cost is proportional to what you're doing. If you're doing a lot of churning on a particular file system, then it's going to make snapshots more expensive to get rid of. But if you have something that's largely static data, like you got this ginormous 12-petabyte movie, but you're not making a lot of changes to it, snapshots are going to be quick because you're not changing a lot of things. So this is a really key point. And I mean, if you ask me what was the one piece of ZFS technology that's like the most insightful, the most useful thing that really moved non-overwriting file systems forward the most, this would be it. Okay, so we'll recap here because I'm just about out of time. The strengths of ZFS: it has really high write throughput because we just drop everything in place. Fast RAID Z reconstruction if we're not making heavy utilization of the pools. We avoid the write hole in RAID. We move the blocks between the file systems as needed. And a lot of the system administration stuff has been integrated in, so you don't have to keep track of gazillions of mount points, et cetera. The weaknesses of ZFS: it requires a lot of resources. You've got to have a 64-bit processor. You've got to have a lot of memory on there. You really want to have some flash drives or memory of some sort on there for things like the ZIL and the ARC and so on. Otherwise, it's not going to run all that quickly. And you need a lot of CPUs to do all the checksumming and other things. The block cache has to fit in the address space. And if you are doing a lot of reading, they just need to fit in the cache because otherwise it's going to be slow because slowly written files are just all over the disk and they're not compact as they would be in an overwriting file system. People argue about this next number, but my claim is that you need to keep your utilization of your pool under about 75%, or you're going to start having some problems with your write performance. RAID Z for small blocks is problematic for the reasons I described. And the cache, the ARC, is not integrated with the memory pool, and so that slows down things that are doing mmap or send file. I decided I'd add a wish list since I have a whole bunch of people here that could actually possibly consider doing this. Both ZFS, or the competitors of ZFS, which are basically Waffle and ButterFS, kinda, maintain back pointers. And back pointers allow a lot of things like disk migration. You can go through and tune up file layouts. If you're working with direct map flash, it allows you to do that effectively. This has been a long, and I understand, big debate with the ZFS people, and I'm not going to try and talk about that, but there is a very nice paper that I've cited here, tracking back references in a write anywhere file system, that it integrates keeping track of the back pointers in a way that would work very well with ZFS, so the cost is low. The cost of actually using it's a little higher, but it's not unreasonable. So there's the reference to that paper, and if any of you are contemplating that, you should read the paper because, if nothing else, it's a great paper. Okay, do I have time for any questions? I'm sort of, okay. I stunned them. Okay. Thank you very much.